What is it that makes Weaviate special in comparison to some of these other things that are on the market?
The big difference, especially for Weaviate, is what we like to call a focus on AI native. We do a lot of education, right? So we share with the outside world, like this is how you build X, Y, and Z. And we spend a lot of effort on that to educate people how to build AI native applications. That is directly inspired through how fashion brands position new products in the market. So there's a direct correlation between fashion and building infrastructure businesses.
And then what types of searches are like vector databases great at? And then what are the limitations? Like where are they not the right solution essentially?
A pure vector search. So with nothing else, a pure vector search is kind of like casting a net in the sea.
Hey everyone, Sean here, and today we have Bob van Luijt, the CEO and founder of Weaviate on the show. I thought this was a really interesting conversation. Bob talks about building AI native applications and what that means, the role a vector database will play in the future of AI applications, and how Weaviate actually works under the hood. We also get into why a specialized vector database is needed versus using vectors as a feature within a conventional database. I love talking to Bob, and hopefully we'll have him back down the road. We barely scratched the surface. And if you enjoy this conversation and the show, please leave us a positive rating and review. And if you ever have questions or suggestions, please hit me or Alex up on social media. All right, let's get you over to the interview with Bob. Bob, welcome to Software Huddle.
Thanks for having me, Sean. Great to be here.
Yeah, thanks so much for doing this. So I was digging into your background a little bit in preparation for this. And, I had heard that you started coding as a kid, but then it looks like you later went on to actually study music in college. So I was kind of curious about what was the original sort of goal or dream with, pursuing something in music?
Oh, the question assumes that there was a goal and there wasn't. So and this is sometimes when I talk, to especially to younger people, it's like when I was young and as in 15, right? That kind of age, 14, 15, until my 20s. There was just a lot of stuff that I liked doing, right? So, and there was just I'm born with a handful of gifts, I guess. And one of them was music, because it turned out that I understood how that worked. So when I auditioned to study music, I was accepted at the conservatory. And simultaneously, I was writing software, and I kind of figured out how to do that on my own, and also around that age. And I also like building businesses around that. To be clear, we're not talking about huge businesses. It was all very small. It was just a young kid, trying to figure stuff out online, and all these things kind of came together. But there was never a grand ambition, right? So it was more like, hey, I am very interested in, I still in art, certain types of literature, certain types of, contemporary art, music, software, those kind of things. I like that kind of stuff, right? So I was the other day, I was browsing through Hacker News. And then I see hey, there was a whole article about the MIDI protocol, right? So between synthesizers and software. And I go hey, that's cool. I love that stuff. So it's I just like these kind of things. And if you distill it, I like to make stuff, right? So I like to make. And now when I'm a bit older, 38 now, that kind of morphed into, software business building, those kind of things. But the original, I guess part of my personality, that this original thing of just wanting to build stuff and explore stuff, that is unchanged. That is still the same. So there was no goal. There was just hey, this is super exciting. I want to be part of this. I want to figure. And what made me very proud is I as part of that, I studied in because I'm Dutch, so I studied in the Netherlands, but then I studied for a period of time in Boston. And there's now musicians that I literally hear on the radio or that kind of stuff that were in school with me there. So it's I'm super proud of that. So it's just riding the wave of life, and then that just takes you in certain directions.
No, absolutely. That's really cool. And then what was your instrument?
So I started with bass guitar. So because it's something you could study, and I was very early on interested in jazz, or like where improvised music, I should say. So that's I started that, and then later, when you do that like a lot, when you study it a lot, then always you always end up. Everybody ends up who studies bass guitar with the same thing, and those are the cello suites of Bach. So, and then at some point you do all these things on your bass guitar. That's, that was like tremendous fun, right? So like a lot of jazz, some classical music when I was older, did some composition, contemporary music, which was wonderful. I had a blast. Was if I could go back in a time machine, I would do it again.
Yeah.
I would buy more Bitcoin though.
Yeah. If we get a time machine, there's probably a bunch of stuff that we both do. A little Bitcoin, maybe invest in Nvidia 10 years ago or something like that.
That kind of stuff. I would change that, but for the rest, I wouldn't change anything. Yeah.
Yeah. And then how did you go from that to founding Weaviate and becoming interested in the vector database space?
So when I was done studying, I wrote software. Actually, I was actually doing art projects that I funded myself by writing software. And in a journey on like just software consult, just freelance. I had a small company, and I ended up at a publisher, and I was working on something completely different related to e-commerce. But back in 2015, they were looking at building new products with machine learning. So that was when I was introduced to Glove. Glove, it's from Stanford. It's still on GitHub, where you could download this CSV file with individual words and then the embeddings, the vector embeddings related to these words. So that was my introduction to that. And I started to play around with that myself. And I had this little idea that I was like, hey, wait a second. If it's in space, then I can take words that might be in a paragraph, calculate a centroid, and store that information. Now, bear in mind, very important to know, this is all pre-transformers that didn't exist yet. But I was like, hey, this is super awesome. So I started to play around with that. I started to present it to people. My first use case was around knowledge graphs in vector space. That was for a long time. People didn't get it. I was like, I remember I even organized my own meetups that again, I funded myself to travel by writing software. And I was like, my first meetup in New York, there were like exactly 0 people showed up. Right. And luckily now it's different, but back then that was the case. And then Transformers came on the scene. I met my co-founder. We figured out, hey, there's room we believe that there's room in the market to build a database specifically for machine learning. And then the whole AI wave took off, and we're just riding that wave. And my co-founder HN, currently the CTO, so still really focusing with the team on the core database. And I became interested in the in the business side of that. So I really doubled down on the business side. Like, how do you build a new infrastructure company in a new emerging market? So that's my focus right now.
Yeah. And then was there some, going back to that, sort of early introduction to embeddings from Stanford, was there also some inspiration or, fascination with semantic web? Like that was also kind of that era of, people are talking about RDF, triples, and all this sort of stuff, and that being sort of the future of how we understand the relationship between objects and concepts.
Yeah, so I've absolutely went through my semantic web period, right? And so the first use case that I would and bear in mind, I'm using the word Weaviate now, but it's by no means was what it is today. But my first use case for Weaviate was an IoT related use case, because I was working on it was like a smart building project where you had like different types of elevators, right, from different vendors, from different OEMs. And the problem was that the data that they were sending in, or through APIs or old fashioned CSV files, the definitions of things in these files or through these APIs, they meant the same thing, but they were not expressed in a similar way. So we created an ontology to describe what was in there, but the problem was we couldn't make these relations. And then I was like, hey, wait a second. What if we use the embeddings to determine the relation in the data set? And so there's absolutely a linked data origin story. And if you go on YouTube, you even find a video on the Google Cloud YouTube channel from maybe 4 years ago or something, where I refer to Weaviate as a knowledge graph. And because the term vector database didn't exist. So, and what we were doing, we're storing data objects, JSON data objects with a vector embedding representing that data object. That is unchanged. That is still what it is today, but it started to focus more and more on the actual vector embedding rather than the data object. Mm-hmm. Long story short, yes, there's absolutely an origin story in the semantic web. And what's interesting is that we're going full circle, because now everybody talks about vector embeddings for knowledge graphs. And I can proudly say, well, I have some videos and material from that from like 4 years ago. So it's nice to see they go full circle.
Mm-hmm. Yeah, I mean, I feel like that those waves in technology is always like what is old is new again. It's like fashion, essentially, like things coming in and out of fashion when it comes to like programming languages, frameworks, all these types of things. Even if you look at neural networks, like there was the sort of AI winter phase where no one was doing any research in neural networks outside of like Canada and a few other places. And now, of course, it's like the only thing that people are focused on. So these things like ebb and flow.
If I can double click even on that. So it's like in the way that we build the business right now around the database, I'm getting a lot of inspiration from the fashion industry, actually. Because one thing that people who might be listening to this, who might be familiar with Weaviate or not, maybe they look it up after listening to this, but they'll see that we do a lot of education, right? So we share with the outside world, like this is how you build X, Y, and Z. And we spend a lot of effort on that to educate people how to build AI native applications. That is directly inspired through how fashion brands position new products in the market. So there's a direct correlation between fashion and building infrastructure businesses.
It's probably a necessary step too when you're building essentially like a new category of infrastructure. Like a lot of people, now I think more and more people are aware of like what a vector database, or at least like have heard the term over the last year and a half. But before that, I'm sure most people didn't know what a vector was, let alone like a vector database. And is growing, but there's still a need essentially to educate the market. And I think the good thing is with the explosion of things like ChatGPT and everything that's happening with transformers and LLMs, it is creating this sort of market force where people are really curious and they want to know what is going on and learn more and more about it.
Agreed. Yeah, 100%.
In terms of Weaviate, like you were, pretty early to the space, but now it's, quickly becoming like a crowded space. I'm sure that was maybe unexpected from where you started, but there's like over, I think like 60 plus databases now that offer some level of vector support, from the like specialized vector databases to things like Postgres and MongoDB that have extended to support vectors. Like, what is it that makes Weaviate special in comparison to some of these other things that are on the market?
Yeah, sure. So the first thing is, I think that's a good thing that this is happening, because a vector embedding is a data type, the vector embedding itself, right? So it's like an integer, a string, a floating point, whatever, right? It's an array of floating points. And so what we start to see is that the majority of that number, right? Let's say you mentioned 60. I lost count. So let's take that as a working assumption, right? 60. So the majority of these 60, they use the vector embedding as a feature. Great. I mean, in Weaviate, you can make a graph connection if you want, right? That doesn't make Weaviate a graph database. It's just a feature that we have that for certain use cases, it helps people to, do whatever we want to do. The big difference, especially for Weaviate, is what we like to call a focus on AI native. And how I always explain that is very simple. You have two types of applications. So first of all, I believe AI is going to be in everything, right? And now you have two types of applications. Application number one is the application where you just, as I like to call it, you sprinkle some AI on your application. So you did a little bit of vector search, maybe did generative stuff. Great. But if I would take the AI out of that application, it's still there. It just misses a feature, right? On the other hand, you have applications that if you take the AI out of the application, it's just gone. It doesn't exist anymore. That's what we call an AI native application. And that's what we focus on with Weaviate. And how do we do that? At the heart, we have the database, and the database, of course, has at its core the vector index, right? That's where it's important. But everything we built around that, uh, uh, hybrid search functionalities, multi-tenancy functionalities, different types of vector embeddings, recommendation engines, the educational stuff that we do, and so on and so forth, is giving people the tools to work with to build AI native applications. And a metaphor I often use, like, think about it like GitLab. So when GitLab started, it was just Git, right? It was just version control. Today, GitLab is there for for your DevOps needs, right? If you're a bank and you have like big DevOps needs, GitLab is your go-to solution. That's what we're doing for AI. So the metaphors where they started with Git, we started with vector search, but we're building this whole ecosystem around it to build AI native apps. So that's the big difference between just having it as a feature versus having it as a core element of the ecosystem that you're building.
Mm-hmm. And what's an example of some AI native apps? Like, I feel like a lot of the stuff that we're doing with AI at the moment feels a little like bolted on. We're kind of like shoehorning co-pilots into everything. And some of those, it's like early days of the internet or early days of mobile, where like people are just kind of like experimenting and trying to figure out like what's going to work. And it took a little while before you really had truly sort of native internet experiences, or native cloud is another example. Like, I remember when I spoke to Bob Muglia, the ex CEO of Snowflake, like one of the things I asked him was there pressure in the early days to do what they were doing on-prem? And was that a hard decision to essentially stay cloud native? And he said it wasn't a hard decision because they didn't know how to do this outside of the cloud. So that was a very like good example of something that couldn't even exist pre-cloud. So what are some things that you're seeing that couldn't exist, sort of without AI being the core part of the application?
Yeah, sure. So I think the easiest way to explain that is by example, right? So let's say that you have a customer engagement system, right? So, support tickets, something like that. An example of just adding AI as a feature might be that you get a support ticket in, you vectorize it, and you try to predict what labels should be attached to the so what department the question should go to, or label, or severity, those kind of things. That's a beautiful vector search use case, and that's a feature. It's a great feature. If you would remove it, then you lose a feature. But that's that's what it is. Now, if we now take the same system, but we turn it into an AI native solution, is still the request comes in, still it gets vectorized. But now, actually, in harmony with the generative model, you start to create what we call generative feedback loops, where actually the model knows how to query the database, requests more information from the database, and writes a response to the person asking the question. Now, if you would take that out of the system, your system just doesn't work anymore, right? So it's the actual models, that's AI natives, the actual models looking in the database to find relative information, formulating an answer, and responding almost near real time. I mean, it's like we can't do real time because the models are not there yet, but let's say near real time, respond to the customer with an answer. That's the difference, right? So where in the first one, it's just a feature, and the second one is truly AI native. If I may add one thing, for the first one, you're probably not going to build a business around it, right? So it's a feature. You're like, hey, we have like a customer engagement tool, and we're going to add this feature. The second one, that's a business, right? There you can say, hey, we can now use the vector database like Weaviate in combination with the models, and just create a completely new application around it that automatically responds based on customer requests, or automatically generates a knowledge base, and so on and so forth. So that's the big difference.
And with this idea of generative feedback loops, like, do you see that as sort of the like natural evolution beyond like where we are with RAG today? Because like RAG is, it works. People are creating applications with it, but in a lot of ways, it feels kind of like hacky. You're kind of like stuffing things into the context to give additional information to the prompt, and then it takes a lot of sort of like testing and iterating to get to a place where you're giving the right amount of context and not too much context and all this sort of stuff. But it feels a little bit, I don't know, like hacky, I think is like the best word I can describe it with. Like, do you see this as sort of like the next phase of that?
No. So I agree. First of all, I agree with that. So, and the second thing is they're actually two separate things, right? So if we separate them up, right? So the generative feedback loop is just a concept of directly integrating or giving the generative model access to the database, basically. That's the concept of the generative feedback loop. That is still something you can do in a hacky way, basically, right? So, but that's the concept. When it comes to RAG itself, right? And if we look at the original paper of RAG, right? The thing is like, can we do retrieval directly from a database based on vector embeddings while we're generating something? Right? Because it's retrieval augmented generation, right? So it's in the abbreviation, and we're doing a lot of work there too. So what you refer to as the hacky way, which again I agree with, is that we get some data from our database, we shove it in the context window, and then we keep our fingers crossed and we hope for the best, right? That's very primitive, right? So, and what's actually happening here, and this is something that I'm a big believer in, is that and this might sound like a sidetrack, but I'll promise I'll bring it back to your question, is that when the context window started to increase, right? So now we have 1 million, and so soon we're gonna probably have 10, 100 billion, whatever, right? So it's like we're gonna get very close to like an infinite context window, and one of the things that people started to say, oh, did the context window kill the vector database? And I think the answer is no, it doesn't. It's actually, I believe, the vector database becomes the context window. Because if you look what a context window does, is that it takes a word. Let's stick to LLMs, right? So let's put multimodality aside for a second. So it takes a word, turns it into a token, gets a vector embedding for the token, creates a matrix, does a prediction, applies the transformer mechanism, does a prediction, turns it back into a token, turns it back into a word. That's very primitive. So what kind of technology is really good at doing that? Well, vector database, right? So this is what we've been with Weaviate, weaving together, right? What we mean with weaving the model and the database together is that we mean that the database becomes the context window. And the moment that the model becomes the context window, you solve that primitive RAG problem, right? So that is and in the slipstream of that, you solve latency issues and all those kind of things, right? So it's operational issues, because just storing a flat, how are you going to do that? Store a flat file or something of like a million tokens? I mean, that's kind of weird, right? So it just makes so much sense to do that more from the perspective of the database. And this is another example of something where it's not a feature. It's just a core element of the database, which is way more AI native, right? So the models and the database, or in this case, Weaviate, they just start to slowly merge together.
And then, outside of RAG, like what are the sort of main use cases for a vector database today?
Yeah, so that depends a little bit how you look at it, right? Because if you use the term use case, right? So it's like you can zoom in, you can zoom out, right? So so at the highest level, the use cases are in the order of that people have been exploring them is vector search, hybrid search, RAG, chance feedback loops. And what do I mean with that, right? So I mean that the first one I mentioned, that's the most that people have in production right now, right? So if you look at our customers, that's the most. And the next thing is hybrid search, right? Because they started to explore it a little bit later. And now we see the first bigger RAG use cases. And then you have the chance feedback loops. And what comes after that are use cases around our graph use cases. And I don't mean graph as in traditional graph, but in graph neural networks, basically, where rather than creating the actual relations, you predict the relations, right? So, but that is stuff that's really new. So nobody has that in production yet. It's really new. So that's the difference. And then if you zoom in, if you say like, so what type of use cases do we see? So we see everything where it's like, it started all with the LLMs. So the LLMs are 90% is text based right now, right? And that is around stuff that is text heavy. So we see a lot of legal use cases, a lot of e-commerce use cases, a lot of um, uh, um, ticket systems, Jira systems, Confluence systems, and so on and so forth. That we see a lot. And people now start to bring the first agents into production. So, but that's more RAG related. So those kind of use cases we see a lot. And from an industry perspective, it's really all over, but especially where it's top heavy on having a lot of unstructured data.
Mm-hmm. And then what types of searches are like vector databases great at? And then what are the limitations? Like where are they not at the right solution essentially?
A pure vector search. So with nothing else, a pure vector search is kind of like casting a net in the sea, right? So you go like, okay, I want to catch a fish. So you cast a net into the sea, and surely you're going to catch fish. But if you're looking for some type of fish, right? So the way that the stuff is organized in the net that's not there, right? So it's like it doesn't rank anything, it doesn't filter anything, none of these things. And then there's the problem that if you search for something where the language you're using, and again, for the sake of argument, I'm going to stick with language models. The language you're looking for was not in the trained model, not part of the trained model. Then it just is like a fish just slipping through the net, right? What's an example of language that was not in the trained model? That can be product IDs, right? There can be names of people, those kind of things, right? Now the good news is that you first want to, there are methods to close the holes in the net, and that's something you can do through hybrid search. So hybrid search that mixes the best of both worlds together. In Weaviate, you can do that out of the box, right? And just like literally 3 lines of code. And so what it does, if I say like, okay, what was the outcome of a ticket that was raised with ID 123 ABC? Then hybrid search will do the traditional search will do very well on ABC 123. And then the vector search will do very well on the whole sentence. So now we've solved that problem. So the answer probably sits in the net. And now we need to start to do the re-ranking and the filtering. And you now see model providers that, so for example, Cohere has like a re-ranker model. At Weaviate, we do a lot of work to make that part of the database itself so that it can train based on the data that you have. But what makes vector search very different from traditional forms of search is that it's more like it casting a net. And then somehow you need to organize stuff as efficiently as you can in the net. That's something we do with like re-rankers and filters and hybrid search and those kind of things. Mm-hmm. Not sure if this is an answer to your question, but
No, that's great. So, I mean, basically, it's great at figuring out that 2 objects are related in some fashion, and essentially the way it's doing that is it's going to have these objects represented in high dimensional space and going to use some sort of similarity metric to determine like they're close in space in some fashion. But it may be not as good at an ID lookup that a traditional database is fantastic at, and it's really what they're designed for. So the key is like, can you bring these 2 worlds together and serve the needs of something that is an index lookup exact match, while also being able to take advantage of these kind of fuzzy sort of similarity type of searches that you also want to be able to do.
Exactly, that is correct. And so actually, a vector database is of the flavor search engine, right? Because storing a vector embedding is easy, right? You can do that. That's just an array of floating points. The tricky part sits in the index, and the index that's used to search and retrieve, right? So, and doing that as efficient and as optimized as possible, that's the trick. That's the core moat of the vector database.
Yeah, so I want to get into the specifics around how Weaviate is doing their vector indexing. So there's all kinds of different ways, essentially, indexing, embeddings. There's cluster-based techniques. There's tree-based index and stuff like that. So what is actually going on in order to generate the index behind the scenes for vectors represented in Weaviate?
Yeah, sure. So I think to answer the question, I think for the audience, it might be who do not know, it might be helpful to quickly say something about what the problem is, right? What problem are we solving, right? So, if you think of vector embedding, right, and you can think of a tiny vector embedding that has like 3 dimensions, so you can imagine that it's in a 3-dimensional space. Is that we want to know what's similar to our query. So let's say that I have 10 objects in my 3-dimensional space, and I have a query, right? So that's one 3-dimensional representation. The way to figure out what's closest is that you take the query 3-dimensional object and you compare it with the first one. I say, what's the distance? And it gives you a distance. You look at the second one, you say, what's the distance? And the third one, the fourth one, fifth one, and so on and so forth. And then when you hit 10, you can just re-rank them and reorganize them based on distance. Like what's the closest, what's the furthest away? The problem with that is that that grows in a linear fashion. So if you now not have 10 data objects, but like 10 million or 100 million, and you don't have, or billion, and you don't have like 3 dimensions, but you might have like 1,000 dimensions, then all of a sudden that takes a long time to actually, it is not real time anymore. So these algorithms were invented, and the abbreviation is ANN, and stands for the approximate nearest neighbor. But they basically, okay, we can come up with algorithms where you can quickly find nearest neighbors, and it comes at a cost. And the cost that it comes at is approximation. So that's why you, for example, when you look at these ANN benchmarks, they always talk about time versus approximation. So the more likely you want the algorithm to be to show the nearest neighbors, the slower it becomes, right? And so this index, like the way that you build it at the core of the database, so in the Weaviate is built on an algorithm called HNSW. And the reason it's built on HNSW is because with HNSW, you can build full CROT support. It stands for create, read, update, delete. That's something you want in a database because there are also vector algorithms that, for example, do not support update or delete. So then you create the index. But if you want to change something, you have to recreate it again. That takes a lot of time. So that's why it's in HNSW. And then you need to figure out, like, how do we short them, right? How do we scale them? And that is the trick of the vector database, right? So that if you run if you have a large use case with like 1 billion data objects with 1 billion vector embeddings attached to that, how do you safely and securely and reliably scale that for your use case? And that's what sits at the heart of Weaviate, and that's what's happening under the hood. And Weaviate is open source, so people can see that. And nowadays we even have like multiple types of these indices, so that you can have multi-tenants and you can offload stuff and put it in memory or keep it on disk. And that all comes with trade-offs. But now, of course, price and those kind of things also start to play a role. So we're pretty sophisticated in the things you can do and how you can scale your vector indices.
Mm-hmm. At what point, you started off by sort of describing the brute force approach of, we have 10 vectors in 3-dimensional space. Like we can just compare everything and figure out what's closest, or maybe the 5 closest, or whatever we need to do. At what point do you need essentially to introduce a vector index? Like how many vectors does it get where this, like a brute force is essentially unscalable?
So, there are 2 answers to that question, right? Often, so you have a use case, and so the audience can think of a use case, right? So whatever use case is, you might have a time limit in mind, right? So let's say that you have an e-commerce use case, then you might say, well, I need to be at least within, 15 milliseconds, I need to be able to present something to my customer. Then it's easy math. So you can just say, oh, I have this number of data objects, similarity scores, brute force, take me X, Y, Z. So, and you would be surprised how quickly you're at 50 milliseconds. So then you quickly need a vector index. But the second part of the answer is more like, when do you need a vector database? And you need a database to keep it reliable, because even if you go like, I just have a couple of data objects, I'm just gonna write a little Python script that just, does similarity search, nothing fancy. What if that server goes down? So a database also comes with all the operational stuff of making sure that it stays reliably available. So the question is not only when do you need the index, but also when do you need to affect the database. And then you just come to the conclusion very quickly that you go like, you know what? I'll just throw it in the database, because if I'm going to write this myself and I want to run this in production, I need to also, take care of the, if shit hits the fan, I need to take care of that too. And I don't want that.
Yeah. Yeah, I guess this is sort of similar math that you would do with conventional databases. Like if you don't have much data, you could store it in a flat file and do a brute force lookup or something like that. And then eventually you're going to reach a point where you're like, oh, I actually need to order these things. So then you're building your own indices that you need to maintain. And then at some point you're like, well, what happens if the file disappears, or, I corrupt the file, or like you said, the server goes down or something like that. And then do I want to, at that point, you're like, well, now I'm actually building a database and then, managed service on top of that. Is that something that makes sense for me to do?
Exactly. There's this little joke in the industry where we say like, building a database takes 10 years. So the first weekend, it just takes you a couple of beers and a couple of friends to come up with the API. And then the last 9 years, 11 months and 3 weeks, you're actually building the database. So it's building database is hard. And the reason it's hard because it needs to be reliable, and building reliable technology at scale, it's just complex. It's hard to do.
Mm-hmm. Yeah. In terms of sharding, like how does the sharding work for a vector database? Like typically with a conventional database, when you're doing sharding, you're picking essentially a sharding index for a particular table. It's going to be based on a column. Maybe it's your user ID or something like that, and then we're going to split based on the ordering of user IDs across different servers. How does that work in the world of vectors?
Yeah, that's an excellent question, and it's like it's actually a bonus question, because it's like there's a double win in this question, because the answer to this question is the reason why vector databases exist in the first place. And because as I mentioned, hey, if it's just an index, but why not add that to like a library, like where we have stuff like Lucene and those kind of things? Why not add it there? And that has to do with the under the hood. And we have a lot of content on this. If you really want to go in depth on this, then we have a lot of content around this on the Weaviate website too. But the problem is this: if you create a shard of a vector index, at some point you need to merge them together, because otherwise the graph just keeps jumping back and forth, and that's just tremendously slow. That's unusable. Some sharding mechanisms use a lot of tiny shards, right? So that they optimize for a lot of tiny ones. And for a vector database, you actually want to have a couple of big ones. So the sharding mechanism is around the bigger shards that you want to merge together. That's very different than, for example, how the sharding mechanism within Lucene works. So long story short, it's an architectural difference. It's a completely new mechanism, how it's sharded. The rest, so there's also in Weaviate, for example, the inverted index and that kind of stuff, that is traditional. Vector index itself is similar. And that's the reason why not only us, but also a couple of other people started to build vector database. People were like, hey, besides the developer experience of interacting with the database being different, also just the architecture is different, right? How we built these kind of databases. And everybody who uses a traditional database for vector embeddings will run into this over time when they scale up. It's just in the nature, and that's not because the existing indices are bad. No, they're amazing. It's just they never designed to deal with vector embeddings. So that is the why these databases exist.
Mm-hmm. Mm-hmm. And then in terms of like similarity computation between two vectors, like there's different approaches there as well, just like there's different approaches to vector indices. Like there's Euclidean, Manhattan, cosine similarity, dot products, all these types of things that have been around for a long time in machine learning space. So how is that done from a developer experience? Is that something that I'm making a choice and I have to decide like how I'm going to compare my vectors, or is that something that's kind of like abstracted away and I don't really need to think about?
Sometimes. So there are two answers to that question. So the first part of the answer is that it depends on the person or the team that created the model, right? So if you look at if you think about a space, right? So you somehow need to organize the data in that vector space. And that can be done on a plane, that can be done in a sphere, that can be done on all kinds of different geometrical systems, right? It's super exciting. It gets very complex quickly too. The reason why these researchers are experimenting with that is because you want to figure out how can we compress as much information in a dense space as possible, and that dictates the distance metric that you need to use, right? So if you're using a vector database and you're getting very weird results, you're probably using the wrong search the algorithm, right? Just the on the other end of the spectrum, the second part of the question is that there are also compression algorithms, right? So a simple example is binary compression, and the fact that a binary quantization works is still fascinating because it's such a simple concept. What it basically does is that if you look at a vector embedding, it's a floating point that's a positive or a negative number. So the first one could be 1.2225 and the second one could be -3 dot whatever. And what a binary quantization does, it's just like, if it's positive, a floating point, we make it a 1. If it's a negative 1, we make it a 0. And what you basically do is that you then search the binary space. So I believe that's the distance metric used for that is I think it's Manhattan distance. I don't know exactly, but that's it's one of those metrics you use. You retrieve a couple of them, and then you do a traditional vector search over these embeddings. And it turns actually out that if you do binary plus a little bit of brute force, you're actually faster than just doing it also in vector space. So now it's a distance metric that you as the user define. That said, we, as from a developer experience perspective at Weaviate, we try to do a lot of work for you there. So we of course, as a user, you can choose whatever you want to use, but we also try to predict and know what kind of distance metrics are needed for you to search through the vector space that you're using. And you might even be storing data from different vector spaces in the same database. And you just want to do a query, right? So you just want to have like a 4-line query and not be too concerned about that kind of stuff. So that's, from a developer experience perspective, we take a lot of work off your plate there as well.
Mm-hmm. Yeah, I mean, I just want to know, like, are these things related, or based on this query, what are the 5 things that are most similar within the database or something like that? The binary use case is interesting. I mean, it makes a lot of sense in terms of you're going to be able to compress rather than using floating point numbers. Suddenly you can essentially take multiple bits and stuff them into like a 64-bit in long or something like that, and then you can take advantage of bit operators on those in order to do the fast lookup, and then that essentially compresses that I guess limits the search space that where you need to do the true vector similarity. So you're using that essentially as a technique to compress, or like I don't want to overuse compress, but essentially create like a bounding box around the number of vectors that you need to do the full vector similarity search against.
Yes, and that is correct. And actually, what you're saying now, actually, something else pops into my mind as well, because inside, for example, Weaviate, you also have traditional indices, but because the database is built from the ground up, from scratch, we also could put a lot of innovations in the traditional indices, right? So like the inverted index is completely built based on bitmaps. So that's a similar system, but then for traditional inverted index. So you can benefit from all these kind of innovations under one roof in one database, and it's exciting. It's very what the core database team is building and the research team it's very sophisticated. And then the trick is, as you mentioned, like how do we take that abstraction away for the end user? That is just a couple of lines of code, and that it just all that niceness comes out of the box.
Yeah. Well, I mean, I think it's a really like fun and fascinating time to be involved in technology, especially if you're working in the AI space, because there's just so much going on there. There's like boundless things to like learn and try and experiment with.
I agree. And it's a, if, if somebody's listening to this podcast and considering starting something, the time is now, right? It's like, hey, don't wait. Start building now because it's such an exciting time. People are excited. People are inventing new stuff. People are, regardless if that's on the low level, in the models or in the vector databases, or on the other end of the spectrum when it comes to the application layer, so much interesting stuff is happening. It's like, this is the time to contribute to that and to, to create a new product or service that, that can ride the AI wave. It's very exciting.
Mm-hmm. Yeah, absolutely. So we're, getting close to time, but I want to start to, we have some quick fire questions for you that we kind of wrap things up with all our guests. So we'll go quick here. So the first one, if you can master one skill that you don't have right now, what would it be?
Singing.
See, what wastes the most time in your day?
Reading boring news websites.
If you could invest in one company that's not your company, who would it be? And we already acknowledged that we missed the Bitcoin bandwagon.
I would invest in CPU companies. I think CPUs are going to play a tremendous important role in model inference in the not too distant future.
Mm-hmm. Yeah. What tool or technology could you not live without?
This is going to be such a boring answer. Oh, my glasses.
Which person influenced you the most in your career?
I would not be doing what I do right now thanks to the many, many people that have advised me and helped me to get where we are right now. So I can't single one person out. It's just, there are too many.
Mm-hmm. No problem. And then the last one, 5 years from now, will we have more people writing code day to day or less?
More.
Awesome. Well, Bob, thanks so much for being here. I really enjoyed this. I feel like we barely scratched the surface here. Well, hopefully maybe we can have you back down the road. I'd love to talk to you about, building an open source business and all kinds of other things as well.
We'd love to come back. Thank you so much for having me. I love the conversation. This is great. And I hope people enjoy it.
All right. Thanks. Cheers.
Thank you.